Ever wondered if traveling into the future could be a reality and not just a sci-fi trope? Imagine for a moment a world where the boundaries of time are as flexible as a rubber band, a place where the past, present, and future can all exist at once. This is the fascinating world of time travel, a concept that has gripped the human imagination for centuries. Throughout history, time travel has been a recurring theme in literature, movies, and television. From H.G. Wells' classic novel, The Time Machine, to the mind-bending adventures in the Back to the Future series, the idea of hopping through time has captivated audiences worldwide. But is it all just a flight of fancy, or could there be some scientific truth to these stories? Well, the answer might surprise you. Thanks to a little something called time dilation, time travel might not be as far-fetched as it seems. This principle, born from the mind of the legendary physicist Albert Einstein, suggests that time is not a constant, but rather, it is flexible and can be stretched or compressed based on certain factors. This is a cornerstone of Einstein's theory of relativity, a groundbreaking piece of scientific literature that continues to shape our understanding of the universe. In essence, time dilation proposes that time can run slower or faster depending on the speed at which an object is moving and its proximity to a gravitational field. So theoretically, if you could travel at the speed of light or near a massive object like a black hole, you might experience time at a different rate than someone standing still on Earth. In other words, while years might pass for you, only seconds could elapse for those back home. And just like that, you've effectively traveled into the future. So the question is no longer, can we travel through time, but rather, how can we harness the power of time dilation to make it happen? After all, the fascinating world of time travel is not just confined to pages of a book or scenes of a movie. What if we told you that time travel is not just a concept of fiction but a scientific reality? To grasp the concept of time travel, we need to first understand time dilation. Time dilation is an intriguing and mind-bending concept, deeply rooted in Einstein's theory of relativity. It's the idea that time, as we understand it, isn't constant. It can stretch and compress depending on how fast you're moving and the gravitational field you're in. Now let's dive into the heart of the matter. Time dilation is an outcome of Einstein's theory of relativity, which fundamentally changed our understanding of the universe. In the early 20th century, Einstein proposed that the laws of physics are the same for all non-accelerating observers, and he added that the speed of light in a vacuum is the same, no matter the speed at which the observer is traveling. This led to some astonishing predictions, one of which is time dilation. At its core, time dilation describes how time seems to slow down as we move faster. It might sound like a science fiction trope, but it's an observable, measurable phenomenon. The faster you go, the slower time moves for you relative to a stationary observer. Consider this: GPS satellites orbiting Earth experience time dilation. They're moving fast enough and are far enough from Earth's gravitational pull that their internal clocks run slightly faster than ours on the ground. This difference is so significant that if not corrected, GPS systems would quickly become inaccurate, leading your smartphone to think you're in the middle of the ocean when you're actually on land. Similarly, cosmic rays provide another example. Cosmic rays are high-energy particles from space, many of which are protons moving at nearly the speed of light. When these protons collide with the Earth's atmosphere, they create showers of particles, including pions. Pions are unstable and decay quickly into other particles. But because they're moving so fast, time dilation comes into play, allowing these pions to travel further before decaying than they would if they were at rest. Time dilation isn't just a quirky side effect of moving quickly. It's a fundamental aspect of our universe, woven into the fabric of space-time itself. It's a testament to the fact that our universe isn't as straightforward as it might seem. It's a world where time and space intermingle, where the speed of light sets a cosmic speed limit, and where time itself can stretch and compress. In essence, time dilation is the universe's way of ensuring that no matter how fast you go, you'll never exceed the speed of light. It's the universe's speed governor, if you will. And it's this that brings us closer to the concept of time travel. So as we approach the speed of light, time slows down for us relative to a stationary observer. And if we could somehow reach or exceed the speed of light, could we then travel through time? That's a question we'll explore in the next scene. The speed of light is not just another speed limit, but a universal constant that plays a key role in time dilation. In the realm of physics, light speed is a superstar. It's not merely a measure of how fast light travels, but rather it's a fundamental constant of the universe. It's woven into the very fabric of space and time. This speed, approximately 186,000 miles per second or 300,000 kilometers per second, is the same for all observers, no matter their speed or direction. This concept might seem counterintuitive. After all, if you're in a fast-moving car and you throw a ball forward to an observer standing still, the ball appears to move faster than if you were standing still. But light doesn't play by these rules. Whether you're standing still, racing towards a light source, or speeding away from it, the speed of light remains constant. This fascinating aspect of light speed forms the basis for the concept of time dilation, a cornerstone of Einstein's theory of relativity. The theory posits that the faster you move through space, the slower you move through time. This is because as you approach the speed of light, time itself begins to slow down relative to someone who is stationary. This isn't a mere theoretical concept, but a fact that has been experimentally verified, with incredibly accurate atomic clocks on fast-moving planes ticking slower than their stationary counterparts. In essence, the speed of light serves as an unchanging cosmic speedometer, the ultimate yardstick by which the universe measures space and time. It's this constancy, this unwavering steadfastness of light speed that enables the weird and wonderful world of time dilation. And it's here, at this intersection of light speed and time, where the tantalizing possibility of time travel starts to emerge. For if time can stretch and shrink based on how fast we're moving, then perhaps we can manipulate time in more profound ways, maybe even to the point of traveling through it. The constancy of light speed is what makes time dilation and consequently time travel possible. Now that we understand time dilation and the role of light speed, let's dive into how this could enable time travel. Picture this. If one were to travel at the speed of light, a fascinating phenomenon would occur. Time, as we know it, would essentially come to a halt for them. Yes, you heard that right. For those aboard this hypothetical light-speed vehicle, time would seem to stop entirely, while the world outside would carry on. This temporal discrepancy would allow the travelers to leap into the future, at least from their perspective. Now you might be wondering, how do we know this? Well, the idea isn't just the product of science fiction, it's a prediction rooted in the theory of relativity, and it's been tested in real-world experiments. One of the most famous of these is the Haffel-Keating experiment. In the early 70s, two physicists, Joseph Haffel and Richard Keating, embarked on an ambitious project. They took 4 atomic clocks, devices known for their exceptional precision, and put them on commercial airliners. 2 of these planes flew eastward, while the other 2 flew westward. Why does the direction matter? Well, the planes flying eastward were moving in the same direction as the Earth's rotation. This effectively increased their speed relative to a stationary observer on the ground. Conversely, the planes flying westward moved against the Earth's rotation, effectively reducing their speed. When the planes returned, Haffel and Keating compared the times on the airborne clocks to those on a stationary clock. The results were astonishing. The clocks on the planes, both eastward and westward, had experienced time dilation. They had ticked slower than the stationary clock, meaning they had traveled into the future, albeit by a minuscule amount. This experiment gave us a real-world demonstration of time dilation, and by extension a glimpse into the potential of light-speed time travel. It showed us that moving clocks run slow, and the faster they move, the slower they tick. If one could reach the speed of light, the clock would stop entirely, allowing them to step into the future. Of course, it's important to note that we can't physically travel at light speed. The laws of physics as we understand them prevent any object with mass from reaching, let alone surpassing, the speed of light. But the implications of these experiments on our understanding of time are profound. They challenge our everyday perception of time as a constant, unchanging entity. They tell us that time is flexible, that it can stretch and shrink depending on how fast we're moving. They remind us that the universe is far more mysterious and fascinating than we can even begin to comprehend. And who knows, perhaps one day we'll find a way to harness this knowledge in ways we can't yet imagine. While we can't physically travel at light speed, the implications of these experiments on our understanding of time are profound. Despite the scientific basis, there are still significant challenges to achieving light-speed time travel. It's not as simple as hopping into a souped-up DeLorean and hitting 88 miles per hour, as appealing as that might sound. First off, let's talk about energy. The energy requirements for light-speed travel are immense. According to Einstein's theory of relativity, as an object approaches the speed of light, its energy needs increase exponentially. To put it in perspective, to power a spaceship to light speed, we would need energy equivalent to the entire mass of Jupiter. It's a tall order, and we're far from having that kind of power generation capability. Then there's the physical toll. The human body isn't designed for light speed travel. Even if we could build a spaceship that could reach the speed of light, there's no guarantee we could survive the journey. G-forces, radiation, and other hazards of space travel would pose significant risks. And that's not even considering the potential effects of time dilation on the human body. And let's not forget about the paradoxes. Time travel, especially into the past, opens up a whole can of worms. Take the grandfather paradox, for instance. What happens if you travel back in time and accidentally prevent your grandparents from meeting? Would you cease to exist, or would you create an alternate timeline? These are questions that science is still grappling with. Beyond the technical challenges, there are also philosophical and ethical implications to consider. If we could travel through time, should we? Would it be ethical to change the past or to know the future? Could we handle the responsibility that comes with such power? These are profound questions which society as a whole would need to grapple with if time travel were to become a reality. There's also the question of what time travel would mean for our understanding of reality. Up until now, we've lived in a world where cause precedes effect. But time travel could turn that on its head, leading to a reality where effect can precede cause. This is a radical shift that could have profound implications for our understanding of the universe and our place in it. In short, light-speed time travel is a complex and challenging concept. It's a tantalizing prospect, but one that is fraught with technical, philosophical, and ethical hurdles. It's not just a matter of building a rocket and blasting off, it's a question of whether we should and what the consequences might be. While we may not be packing for a trip to the future just yet, the concept of time dilation and light-speed travel continues to push the boundaries of our understanding of the universe. So where does this leave us in our understanding of time and the possibilities of time travel? We've delved into the enigmatic world of time dilation, a concept that shakes up our conventional understanding of time. This mind-bending theory, a brainchild of Einstein's theory of relativity, suggests that time isn't a constant entity. It can stretch and compress depending on the observer's speed and gravitational field. We've navigated the speed of light, a cosmic speed limit if you will. Clocking in at an astounding 186,000 miles per second, it's a speed that's seemingly untouchable, yet it forms the crux of our discussion about time travel. We've entertained the tantalizing idea of light-speed time travel. If we could somehow harness the power to travel at light speed, we could theoretically slow down time, allowing us to journey into the future. A concept that may sound like the stuff of science fiction, but it's grounded in real-world physics. These concepts challenge our conventional understanding of time, pushing the boundaries of what we thought was possible. They invite us to entertain the notion that time, as we understand it, isn't set in stone, that it's malleable, capable of being manipulated under certain conditions. Yet, as we've discussed, these concepts don't come without their challenges and implications. The physical demands of achieving light speed, the ethical considerations of time travel, the potential for time paradoxes, and the profound implications on our understanding of reality itself. This journey of understanding time, of peeling back the layers of its complexities, has been a fascinating ride. It's a journey that continues to captivate scientists and enthusiasts alike, inviting us to dream, to question, and to explore the mysteries of our universe. While the journey towards understanding time and potentially traveling through it is filled with complexities, it's a journey that continues to captivate scientists and enthusiasts alike.